Hello, my name is Dr. Maria Weber, and this is your mini lecture about circuit analysis and Kirchhoff's rules. Now, the circuits that we are working with are about to get a little bit more complicated, but luckily we have Kirchhoff's rules in order to help us solve some more complicated circuits that we're going to see. So Kirchhoff has two rules, and the first one is called Kirchhoff's junction rule or junction law. And it states that the total current into a junction must equal the total current leaving the junction. So let's say we have our circuit and we have three wires that are kind of coming together at this junction here. And so what this is saying is that the current coming in, which we'll call I1 here, has to equal the currents coming out. And so if we say that I1 is equal to I2 plus I3 in this example right here. And you can think of it as kind of like a stream, and then it divides, and the current coming in through the main branch of the stream has to divide to go down those other two branches of a stream. And if the current, and certainly the current coming in, is going to be greater than the current that ends up coming out through the other two branches here. And so the example for the junction rule for this example right here, we have I1 coming in and then I2 and I3 coming out. We would say I1 is equal to I2 plus I3. Now this junction rule is a result of charge and current conservation. What comes in must be the same thing that comes out. And we can write that as a more formal equation here as the sum of all the currents coming into a junction has to equal the sum of all of our currents coming out of the junction. Now, Kirchhoff also has a second rule, and sometimes we refer to this as the loop rule. Now, for any circuit, if we add all of the potential differences up around the loop formed by the circuit, the sum of those potential differences must be zero. And so we can write that as the sum of all the potential differences around a loop that we can draw within our circuit must equal zero. So for example, we have a circuit right here. We have four devices, whatever they happen to be, that have some potential difference across them. Let's say that these are all batteries. And so we can start our loop wherever we want. We're going to start the loop right here. And so then we would say that as we're moving around this loop, that the sum of the potential difference across this first device, plus the sum of the potential difference across the second, plus the third, plus the fourth, that all has to equal zero. And so we have a particular formalism that we use with the way in which we use our potential differences around the loop, and whether or not we call them positive or negative. So here we have a circuit. We've got a battery supplying some EMF. We've got the negative terminal here, the positive here, and then the direction of the conventional current within the circuit is going to flow around in this direction in which this loop has been drawn. And I like to draw my Kirchhoff's loop from negative to positive end of the terminal, and so my current is going to be moving around this loop in this direction. We start at the negative end and move through the positive end of our terminal and move around. This is the direction of the conventional current, okay, which we call the positive current. Now, as we move from a negative to positive end of our terminal battery, we are increasing our potential if we're moving in the direction of current. And so as I'm moving from the negative to positive end of the terminal, I'm going to call that a positive potential because we're increasing our potential here. Now, as I go through in the direction of current, resistor 1 and resistor 2, if I'm moving through them in the direction of the current, my potential is actually decreasing. So if I'm moving through R1 and R2, I'm going to represent those in an equation as negative the potential difference across this resistor and negative the potential difference across this resistor. So if I were to create or write down the Kirchhoff loop for this circuit here, I would say that the positive EMF coming from the battery minus the potential difference drop across R1 minus the potential difference drop across R2 equals 0. And this is a really great graph that shows the potential around our circuit. So here we're at our battery and we're moving from the negative to positive terminal of our battery, and we see that the EMF goes up to its maximum value. And then as we move through resistor 1, our EMF, our potential around the circuit decreases. And then as we move through R2, our potential also decreases. And so this would be a chart that you could draw for the potential around the circuit. And so then the sum of all of these around the circuit has to equal 0. And so once we started going through the negative to positive into the terminal and around, we're back to 0 again. Okay, so we're going to use Kirchhoff's two rules, the junction rule and the loop rule, in order to solve the next two problems. And so I'm going to consider this circuit right here, and we're going to find the current I1. So here I have my EMF source, and it's supplying a current to my circuit, the potential difference to my circuit. And so the current that I'm calling I1 is coming around here. It's moving through resistor 1, and it's encountering this junction right here. And then it splits off, that current splits off into two paths, and part of it splits off, and what I'm calling I2 goes through resistor 2, and then the other part of it splits off, and I'm calling that R3. R3 goes through resistor 3. And so current I3 here, current I2 up here, they combine here at this junction, come back out, they sum together to give me I1 back again, okay? And so we are going to draw in Kirchhoff's two Kirchhoff loops. So we're going to draw in two Kirchhoff loops into the circuit. We're going to put one here, and we're going to put one up in here, and we're going to use the junction rule plus these two loops in order to get three equations to represent what's going on in our circuit here. We're going to use those three equations, and we have three unknowns, which are the the currents through each of our resistors. Three equations, three unknowns, and then we're going to use those to solve them in order to find the current through each of these individual resistors. Okay, so we're going to go through this circuit problem here using a method that we call circuit analysis, and we're also going to use Kirchhoff's rules in order to help us find what we're looking for in the end, the current I1 in our circuit. And in order to do that, we have to find the currents I2 and I3 through our circuit. So here I have a 6-volt EMF, and it's connected to, we have one resistor right here, 4 ohms, and then the wires branch off so that we have two resistors here in parallel, one with a resistance of 5 ohms, another with a resistance of 9 ohms, okay? And so here I've drawn it so that the current that I'm going to call I1 moving through this first part of our circuit comes to this junction here, and it branches off into two currents, one that I'm calling I2, which goes through the top loop here through resistor 2, and the other called I3, which goes through our third resistor here. Okay. And so this actually gives us our first equation that we're going to use to help us solve for the current I1 in our system. And this first equation is coming from Kirchhoff's junction rule. So here we have a junction where we have our wires branching off into 3 different directions. And so our current I1 coming in through here has to equal the sum of I2 plus I3. And so the junction rule says that any current coming into a junction, the sum of all those currents must equal the sum of all the currents coming out of our junction. Okay? And so I'm going to call this equation 1. Now we have to use Kirchhoff's second rule, which is about Kirchhoff loops, in order to get our other 2 equations that we're going to start with here in our problem. So we have loop 1, which I'm going to draw this direction around my circuit here. And so I'm going to assume that I'm going to start here with my EMF.
And as I move from the negative to the positive terminals of my voltage source, we are gaining potential. So we would call that a positive potential gain with positive value here. And as I go around my loop here, and as I go through resistor 1, as we go through resistor 1, we are decreasing our potential, and so we would write that as a negative potential in an equation. And then as I go again through around my loop, I'm going to go through circuit 3 right here, so I would also be encountering a negative potential or decrease my potential here, and then come back around to my battery. So Kirchhoff's loop rule says that the sum of all the potentials around our loop here has to sum to 0. So if I use this first loop that I drew here, I'm going to call that loop 1, and I use Kirchhoff's loop rule here in order to write an equation down to follow along my loop 1 here, I'm going to have the potential from my EMF minus the decrease in potential as we go across the first resistor. And as I'm going through here, I'm following along my loop, I'm going to go through with the current through resistor 3, and I'm going to decrease my potential. So I'm going to put minus V3, and that all has to equal 0. And I'm going to and that all has to equal 0, and I'm going to call that my second equation here. Well, I'm going to make another step. Here, because we know that V is equal to IR, I'm going to replace V with I1 R1. Okay? So my current running through resistor 1, I called I1 here, so I can replace that with I1 times R1, minus, as I'm following along my loop here, I encounter the junction, and I go through here, through my third resistor. The current through my third resistor I'm calling I3, and so I'm going to write that as minus I3 R3, and that equals 0. So as I'm following along my loop, I'm also following along in the direction of my current, at least for loop 1 here. Okay? And so I'm going to call this equation right here equation 2, which I got by following along the loop from my first loop here in that I can draw within my circuit. Okay? Now I'm going to draw a second loop up here. And I'm going to call this loop loop 2. Okay. And so loop 2 starts here by me going through the third resistor, around through the second resistor, and back again. Okay, and so if I use Kirchhoff's loop rule for loop 2, I will have, so we're going through this resistor opposite the direction of current. And whenever I'm moving through my loop opposite the direction of current, I'm actually not decreasing my potential, I'm gaining potential. So this, I would say, is positive V3. And then I come around this loop and I go through resistor 2 in the direction of I2. So in that case, I'm decreasing my potential. So positive V3 minus the potential across resistor 2 equals 0. And so if I replace these voltages with IR, this is going to look like positive I3 R3 minus I2 R2, and that equals 0. So that will be my third equation. So using these 3 equations here as our starting point, we've got 3 equations, 3 unknowns I'm looking to solve for. We can use these 3 equations in different ways in order to get at I1 right here. So there's going to be a little bit of algebra in the next amount of work that we're going to do. So usually I encourage you to start with your equations and keep them in their algebraic form for as long as possible. But in this particular situation, when we're doing circuit analysis, I'm going to say, let's go ahead and replace all of the values that we possibly can with numbers right now. And we're going to replace them with numbers, and what we're going to do is we're going to solve this second equation right here for I3. Okay? And then we're going to solve this third equation here for I2. And you'll see why I did that here in a minute. Okay, so I'm going to start with equation 2 here. My EMF in my system is 6. And just to keep us from getting confused with all the different V's floating around here, I am not going to put in the units on these values, okay? So I've got 6 as my EMF minus, my first resistor is 4 ohms, so I'm just going to say 4 times I1 minus, my third resistor is 9 ohms, so 9 I3, and that equals 0. Now I'm going to solve this equation here for I3. And if I do that, I'm going to add this term over to the other side. So I'll have 9I3 equals 6 minus 4I1. And then what I'm going to do is divide both sides by 9. And in that case, I get that I3 equals 0.67 minus 0.44I1, okay? And I'm going to call this equation 4, all right? Maybe I'm going to sort of draw a dotted line here to keep all of our work separated. And now when I come over here to our equation 3, I'm going to plug in my values here. So R3 was 9 ohms, so 9 times I3 minus R2 is 5, so minus 5 I2 equals 0. And I wanted to solve this equation for I2. So if I do that, then I have that I2, if I add 5 I2 to the other side, 5 I2 is equal to 9 I3. Divide both sides by 5, and I have I2 is equal to 1.8 I3. And I'm going to call this equation 5. Okay, so I started with my first equations 1, 2, and 3. I did a little bit of work, some algebra, in order to get my equations here 4 and 5. Now, I told you that there was a lot of algebra here with this problem. Now, for my next step, what I'm going to do is I'm going to take equation 1 right here, and I'm going to put substitute equation 5 into equation 1. So when I do that, I'm going to get that I1 is equal to, where I have I2, I'm going to put 1.8 I3 plus I3. Okay, so I substituted equation 5 right here into equation 1 for I2. And so if I do that, now I've got a new equation that tells me that I1 is equal to 2.8 I3. And I'm going to call that equation 6. Okay? So I'll tell you exactly why we did it this way. If I go back to equation 4 right here, I've got I3 is equal to 0.67 minus 0.4 I1. Okay? Now with this equation here, I don't know what I1 is, but I just found an equation for I1 in terms of I3. So I'm going to take this equation right here, equation 6, and plug in this value for I1 is equal to 2.8 I3 into equation 4. So now I'm going to say that I3 is equal to 0.67 minus 0.44 times my value right here, 2.8 I3. Okay, so if I do that, then I get that I3 is equal to 0.67 minus 0.44 times 2.8, and that's minus 1.23 I3. Okay, almost there. Now if I add negative 1.23 I3, if I add that term to the other side, then I will have I3 plus 1.23 I3, which gives us on this side 2.23 I3 is equal to 0.67. All right, now I have to divide both sides by 2.23, and I get that I3 is equal to 0.67 divided by 2.23, which is 0.3 amperes. So finally, I got one of those values. I3 is 0.3 amperes. Now, I can take this equation right here, or this value for I3, and I can look back at any one of these equations, in particular equation 6 and equation 5. So equation 5, I've got I2 in terms of I3. Equation 6, I've got I1 in terms of I3. So what I can do now is I can plug I3 into equation 5, and I'll find that I2 is equal to, let's put a little dotted line here, 1.8 times I3, which is 0.3 amperes. So 1.8 times 0.03 gives us 0.54 amperes for I2. Okay, I2, 0.54 amperes. Now, for I1, I can take my equation, or my value for I3, and plug it in right here. So I1 is equal to 2.8 times 0.3 amperes. So 2.8 times 0.3 gives us 0.84 amperes. So I1, finally, right here. And so I1, 0.84 amperes. Now, if I take I2 and add it to I3, I also get back I1. And that's exactly what we wanted, because if we go back and look at our first equation for Kirchhoff's junction rule, I see that I1 is equal to I2 plus I3. And by doing all this algebra work, we eventually showed that, in fact, yes, I2 plus I3 does equal I1. So I know that it's a lot of algebra work. The homework problem that I'm going to give you is the exact same process here, you just have different numbers. And so the challenge is to follow along with this problem-solving process. And it's kind of like solving a puzzle. You want to look at these equations and figure out how you can solve them in different ways in order to eliminate some of those terms and eventually get out at least one of those currents, so that you can take that value and plug it into any one of the other equations in order to get our three values that we're looking for current. And so if we've got three equations and we have three unknowns inside those equations, we're able to go ahead and solve for any of those values for our current.